Our next talk is from Anshuman Mohan on distinguished paper, the title Formal Abstractions for Package Scheduling. So over to Anshuman.
Thank you. You may have heard of this hip new thing called software-defined networking, which made networks programmable. So an early goal was routing, and that was all nice, but now you want a little bit more. You want control over packet scheduling. So here we are in Qashqai, and packets are coming to us from either Hibamar or from Barheo. And I want to know in what order these packets will be released from me, because I'm just a waypoint, they're going on from me. Okay, basic tools will sort of work fine. So imagine in my Qashqai-based packet scheduler, in my switch, I have a FIFO, just first come, first served. I can do basic buffering, life is good. I can do a little bit more. I have a PIFO. PIFO is just networking speak for a priority queue. I can do a little bit more programming, nice. But actually, modern scheduling requires quite a bit more, often in terms of hierarchical scheduling algorithms. So say every packet that came from Hibamar is either headed to Porto or to Torres Vedras, and I've been asked to interleave red and blue packets, and among red packets also interleave purple and tangerine packets. I'm in a bit of a fix, actually. My PIFO is not going to be able to handle this, but thankfully, from SIGCOM Valhalla, I've received a PIFO tree. This is a mythical beast. It doesn't actually exist in reality, but it's been given to me gratis for the purpose of this talk. And it totally solves the problem, right? This is a tree-shaped challenge, and I have a tree-shaped solution. Great, life is groovy. In fact, the PIFO tree can even do more than I've asked. It can do arbitrary sort of sharing, not just equality. It has state. Very, very nice. The day is saved. Sadly, the user says, look, everything worked fine. You did what I asked, but I was still seeing congestion because large packets were sort of clogging up the works. I want to split up my flow in a different way. Please interleave small, medium, and large packets, and then do some more stuff among the small packets. That is my new request. Look, my PIFO tree is totally going to keel over and die. It just can't conceive of splitting the flow 3 ways. It's intimately tied to the notion of splitting 2 ways, and then 2 ways again on the left side. You don't know what a PIFO tree is. I appreciate that. I'll solve that shortly. But already you can appreciate, what you can appreciate is how unsatisfying this problem is. Right? This is a nice gadget. It can do a bunch of stuff, but it fails in an unsatisfying way. And I've not just sort of made this up. And users are going to want to program the trees in all kinds of ways. And the hardware, which does not turn on a dime, is going to want to build one thing and deploy that. And I'm going to have to make a connection between those 2 things. And that's what this work will do. I'll show you what to put on all your hardware and how to get there. All right, time to talk about PIFO trees. This is I'm still trying to solve the red, blue, purple, tangerine challenge from earlier. I have a tree-shaped gadget, and all my nodes are PIFOs, priority queues for our purposes. In my leaves, I'm carrying packets. These are the colored things. In my other nodes, I only have the one right now. I'm carrying indices. In particular, I must carry 2 instances of the number 1 because there are 2 things in my first child, and I carry 3 instances of the number 2 because there are 3 things in my second child. Of course, the order of those is up to me. That's just a PIFO doing its thing. If I honor this stuff, then my PIFO tree is well-formed, and a well-formed PIFO tree is a real cool thing because it behaves like a queue. It can be pushed into and popped from. Let's do both of those things. How do we pop it? You pop the root. Out comes the most favorably ranked item, which in this case is rendered on the far right. So the 1 comes out, and this triggers the popping of my first child, and what comes out? P1. This is the result of popping this tree 1 time. Let's do it again. Pop. 2 comes out. Pop. B1 comes out. If you do it all the way, that's what you get out. And I'm going to put the tree back for you, but this is the logical state of the tree. This is what the tree is sort of trying to say. I'm going to put these bars over the purple packets just to show you that those are actually also red packets. This will become germane shortly. Let's push into this tree. So our tangerine packet, the first tangerine packet is arriving, and where does it go? Well, it's going to go into this suggestively red-colored left leaf, okay? And because I have a chance to sort of get some justice, I have 2 purple packets in a row, and I have a chance to put a tangerine packet in there. I'm trying to get parity, so it sort of suits me to put that tangerine packet between them there. This tree is no longer well-formed, and I owe the indices, I owe the root a 1 to make it well-formed. And again, it suits me fine to put that 1 between those 2 2s, and therefore achieve parity. Okay? So this tree is well-formed. It has fully accepted my tangerine packet, and just to show you the state of this tree, it looks like so. And I put those bars back on there for you to show you what a blue packet is and a red packet, and then further to red packets, we have tangerine and purples. And I've successfully accepted this tree indeed, because look, I have red and blue interleaved, and further purple and tangerine interleaved. Something quite subtle had to happen along the way, though. B2 and P2 have swapped places, and I didn't do that in front of you. It sort of happened as if by magic. It happened because of this, because I, T1, was popped not by the one that I inserted, but by some other one. And the one that I put into that queue with my own hands in front of you has triggered the popping not of me, but of somebody else. Like that. This on-the-fly switching of targets is what gives PIFO trees their power and expressivity, and can do stuff that a PIFO can't just do. It also makes them a pain to study. If I lost you there because it was all sitcom stuff, please come back. We're going to get into PL land now. The key insight here is that a PIFO tree, by its very shape, manifests a programming language. And a program written using that programming language is precisely a scheduling algorithm. In particular, when a blue packet's coming in, what's actually happening? My program is looking at the packet, looking at its state, etc., and then figuring out a path with which to insert this blue packet. I'm going to have to put a 2 in there with some rank, R1. R1 is the rank with which I'll insert the number 2 into my root, and R2 is some rank with which I'll insert the packet B1 into my right child. I'm obfuscating what R1 and R2 are. For our purposes, they are just the ranks I needed to put the thing where I wanted it to go. Right? So 2 went somewhere, B1 went somewhere in that queue. Great. And you're sort of seeing a connection between the shape of a tree and the expressivity of the language that the tree manifests. And now we're really cooking with PL gas, okay? Because can we compare the expressivity of languages? Well, can I affect the same permutations on the incoming flow that you can? Can I compare expressivity of trees? And sort of the pièce de résistance, can I compile a program written against one tree so it instead runs against a different tree of a different shape? I'm not just doing this for my health. This is going to solve our problem, right? We had no way to deploy our gadget. I'm going to tell you what tree, some sufficiently expressive tree, to put into all your switches and how to get there via compilation. Right? So crisply, the contributions of the paper are the first formal model of the PIFO trees, general theorems of expressiveness with regards to tree shape, the compiler I just mentioned, and a simulator to aid experimentation. The talk is not the paper. I will lead with the compiler and give you the rest as I need to. Okay. Expressivity of trees basically follows your intuition. If you fix a particular height, trees with more leaves are more expressive. If you fix a particular arity, then taller trees are more expressive. This quickly gets out of hand, actually, when you have bigger and bigger trees, but thankfully it's all captured nicely by our new notion of homomorphic embedding, which is to say, try to find, so here's my source tree and my target tree, try to find a map from nodes to nodes, trying to get the root to map to the root, leaves to leaves, and as you do so, respect ancestry. So here's a successful case of homomorphic embedding. Here's a hairier case, but let's look at the simpler case because I'm going to show you a little thing about it. So the point here is that the target tree, if you believe me, can accept the source tree. It can say what the source tree is saying. It can affect the same permutations. But by failing spectacularly in the next slide, I'm going to show you why it's a little trickier than you think. So let's try sort of a simple case. The tree on the left is just trying to do parity among its 3 children, red, blue, and green, with those equal signs. And I've told you to please try and get the same behavior on the binary tree on the right. All right? The first approximation, you might say, okay, just do it 1/3 and 2/3, and among the right node, do 50-50. Right? This seems to work at first. You know, if everybody is chatting, this actually will work. But consider what happens in case of silence. In case the blue flow fell silent in my source tree, my oracle tree, then the red and green would correctly share what remains 50-50. This is what I want. However, on the right, if blue fell silent, green would totally take over the entire right half of the tree and dominate red 2/3 to 1/3. The point is, there's a little more to it than you think. All right? Basically, I had a root, and I copied over the root sort of faithfully, but I've had to insert this transient node just to make the shape work. And my point is that trying to give the transient node any standalone policy like we just tried is always going to fail. It's going to be subverted by some sort of unfriendly flow of packets, usually full of silences, that will sort of hurt me. Right? The observation is that the root on that receiving tree really still has 3 children, red, blue, and green. And we're all still on talking terms, no problem. It's just that my children, blue and green, have left home and gone to college. They live out of state now. Okay? And earlier, I used to be able to reach blue by just saying, 2, and now I reach blue by saying 2 and then 1, right? Keep that intuition in mind as I crisp this up on the next slide. So I've given us some numbers in the root node now. I'm trying to achieve parity as before. And the way to actually copy this over, actually make the compilation work, is it proceeds in 2 steps. I'll do it node by node. So for the root, I copy over the queue, sort of ranks and all. Ranks I'm not showing because they're sort of baked into the way I've drawn it. That queue has been copied over, but I'm in the wrong addressing regime. We already know every time I say 3 or 2, I really mean 2 and then something. So I renumber to change all the 3s and 2s into 2s, like so. And for the transient node, I'm going to copy again, but I have no heirs of being able to reach red anymore. I have no 1th child as before, so I copy it over, dropping all 1s, like so, and then renumber for the new addressing regime, like so. So this different style of copying is resistant to silences and sort of adversarial packet flows. It's really illustrative to look at a push going through, so let's look at that. If a blue packet were coming in the oracle tree, I would have assigned some path to it, starting with 2 and some rank R1, and then something else, okay? What do I do in the receiving tree? So the 2 went in, and I achieved parity. You can see 3, 2, 1, 3, 2, 1, 3, 2, 1. Very nice. And in the receiving tree, that same B is going in, right? And you all already know that we're going to have to put a slightly longer path in there, starting with a 2 and then some 1. The question is, with what ranks? And here's the great news. The answer is actually real clean and simple. Use the same rank, R1, as the original tree would have. And as if by magic, my 2 will slip into the right place, my 1 will slip into the right place. Why has this happened? Because I followed my queue, I copied my queues over faithfully, just changing numbers cosmetically, keeping the ranks around. So we were given an embedding from a tree shape to a tree shape. We were able to lift it to now operate on a brain, compiling to a brain, automatically generated. But why should we be given an embedding? Let's just make our own, right? So remember, this is what we're aiming for, trying to get these dashed lines, trying to get these homomorphic embeddings automatically. I have 2 algorithms for you, and they both start with heterogeneous source trees, by which I mean I don't actually make any assumptions on the arity or regularity of my source tree. If you tell me that your target tree is a regular D-array tree with some arity D, I have an efficient algorithm which will actually construct for you the minimum height D-array tree that can accept your source tree. If you bring your own tree, it's a heterogeneous tree, it's a wild tree, I have another algorithm less efficient which can tell you if a mapping is possible, and it gives you the mapping if so. So what's the workflow of somebody trying to actually use all this stuff? Say they had this dream. It's a 3-tier hierarchical thing with 7 different flows being managed. WFQ and RR are different scheduling regimes. We won't get into it. This is their dream, right? But they are told that the hardware only supports a regular branching binary tree. No problem. We know how to instantiate it now. We'll use the first algorithm I mentioned to create the minimum height binary tree that will accommodate my tree, and then I'll instantiate it as my compiler suggests, like sort of so. This is automatically generated with an automatic brain, which I didn't have to write by myself. Okay? And now we can sort of look at all this stuff, go through a simulator, which is also a contribution of our work. So the point of the simulator is that it can take a pcap of packets and run it through a PIFO tree and show you what would happen if the PIFO tree were to schedule those packets, including like overtakes and delays and so on. So simulating the first tree, the logical desire shows us sort of this. This is a hip new way I'm trying to visualize schedulers. I hope the community catches on. But basically, shorter bars mean better performance. You were held up by the scheduler for a shorter time. Longer bars mean worse performance. The scheduler held you up for a longer time. A bar sort of starts when the packet enters the scheduler, and it ends when the packet is released, right? So that's the result of simulating the first one. And this, the second one, they are the same picture. Great. Why should you believe any of this? Well, we have an underlying formalism. Here I'm just showing you what it takes to sort of chase a push up the entire formalism. It really is better appreciated in the paper, so I'll send you there. I will say there's no point in the paper where I have a horrible picture like this. The paper does quite a nice job gently introducing you to all this stuff, so I do recommend it. But the point is that we've solved our problem. We have a general way to deploy PIFO trees. Let the hardware support some tree, and let the user program against some tree. Today they want that. Can I compile it? Well, yes, I can, into that fragment of my target tree. So please light up that much, and I'll do my business on that. They wake up the next day, they want something else. I compile again and see, is it going to fit? Yes, it is, into that fragment. And so again, life is good. I can go on. But the next day they want that, and I check if it's compilable. Oh, no, it's not. But now I can go to my user and give them a little bit more information. I can say, oh, look, you had too many leaves, or your height was too much, or whatever, and they can sort of adjust. And if it turns out that like millions of users all need something that the hardware cannot provide, we can ask the hardware providers for some change in a sort of an informed way. We're not just nitty-gritty, not just being flip and asking them to make new things for us every single day, right? This has been Formal Abstractions Packet Scheduling. I've been Anshuman Mohan. I'm happy to take any of your questions.
You have time for a couple of questions.
Okay, at the end, those checks and X's went by a little bit quickly for me. So what are the formal properties that the system satisfies? Is it sound and complete?
So for the first algorithm, where I was telling you about a tree being constructed for you, basically it's always going to work. I'm always going to be able to construct a tree of your desired arity. It just may be awfully tall. It may be taller than your hardware sort of supports. Mm-hmm. And so I might say, look, it's not going to fit into what's actually provided. Yeah.
Okay, and then when you say it doesn't fit, there is no fit. If your tool says that there is no fit, I can't compile it down to this hardware. That's
accurate. Yeah.
That's accurate too.
Yeah.
Okay, great.
Yeah.
Any more questions? Well, I have a quick question. Okay, let's thank the speaker again.